In 1687, Isaac Newton published Philosophia Naturalis Principia Mathematica, and for the first time described gravity using modern mathematics. And from then on, almost everyone thought they understood gravity. You know, the apple fell on Newton's head. Then he discovered the force of gravity. The story sounds very neat and complete. But here is the strange thing. Newton never actually said what gravity is. He only wrote down the equations that describe how it works with astonishing accuracy. Honestly, even in the 1980s, physicists like me still did not fully understand gravity at the deepest level. We could calculate the orbits to send the Apollo spacecraft to the moon accurate to the kilometer. But if you ask, what is gravity really? The answer became surprisingly uncomfortable. And the deeper you look into gravity, the more reality begins to behave in ways that are almost absurd. And this is where things start to get really weird. In the 1980s, physics recognized four fundamental forces of nature: the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. The strong force holds protons tightly together inside the atomic nucleus, even though they all carry positive charge and are constantly pushing each other apart. The weak force is responsible for radioactive decay. Electromagnetism powers electricity, radio, chemistry, light, and almost all the modern technology you use every day. And gravity? Gravity is the weakest of all of them. So weak it is almost ridiculous. Think about this for a moment. An average adult can easily stand up from a chair, lift a cup of coffee, or jump off the ground, even though the entire planet, weighing about 5.97 times 1024 kilograms, is constantly pulling them down. A small magnet weighing just a few grams can lift a paper clip off the table and overcome the entire gravitational pull of the Earth. That is far more astonishing than most people realize. The electromagnetic force between two electrons is stronger than gravity by about 1,036 to 1,038 times. Honestly, sometimes physicists look at gravity and feel like there is something wrong with it. It is inexplicably weak. If gravity were a character in physics, you would almost think it does not belong in the same universe as the other three forces. But then the paradox appears. This very weakest force creates stars, galaxies, planets, and the entire large-scale structure of the cosmos. If gravity were a little stronger, stars could burn their fuel too quickly and the universe would become extremely violent. If gravity were a little weaker, the hydrogen clouds after the Big Bang might never collapse enough to form galaxies or stars. Somehow, the entire universe is built from the weakest force in nature. And what makes gravity truly scary is not its strength. What makes it special is that it never really disappears. The strong nuclear force, the strongest force in nature, only operates at extremely short distances, about 10·15 meters, roughly the size of an atomic nucleus. A little farther away and it almost completely disappears. But gravity does not do that. Gravity operates at infinite distances. That means every object with mass in the universe is gravitationally affecting every other object, no matter how unimaginably far the distance. Technically speaking, your 70-kilogram body right now is still pulling on the stars in distant galaxies. Of course, that effect is extremely small, so small it cannot be felt, but it exists. And that is the important point. Newton described this with the inverse square law. When the distance doubles, gravity decreases to 1/4. Triple the distance, and it becomes 1/9. Gravity weakens very quickly, but it never truly becomes zero. Look at the moon. It is about 384,400 kilometers from Earth, a huge distance by human standards. But its gravity is still strong enough to pull the entire oceans up and down every day and create the tides. Honestly, that is already quite strange. But what is truly important is that gravity never shuts off. It never stops. And when a force operates continuously over millions or billions of years, even an extremely weak force can change the entire universe. After the Big Bang, the universe was mostly enormous clouds of hydrogen and helium. Gravity was very weak, but it kept pulling the particles closer together non-stop over enormous spans of time. Gradually, those clouds collapsed into stars. Stars clustered into galaxies. Galaxies created the cosmic structure of the entire observable universe. Our sun contains about 99.8% of all the mass in the solar system, and its gravity has kept Earth and the other planets in orbit for billions of years. Earth is flying around the sun at about 30 kilometers per second. If the sun's gravity suddenly disappeared, Earth would not continue orbiting, but would fly straight out into space along a tangent, just like a rock released from a spinning string. But this is where things start to get stranger still. According to Newton, gravity seemed to act instantaneously. If the sun moved, Earth would feel the change immediately. Einstein realized that could not be right, because in relativity, no information can travel faster than the speed of light, about 299,792 kilometers per second. That means gravity must also have a propagation speed. Light from the sun takes about 8 minutes and 20 seconds to reach Earth, and gravitational influence does too. If the sun somehow disappeared right now, Earth would still continue orbiting the old position for about 8 more minutes before the space-time disturbance arrived. Think about that for a moment. Gravity is not an invisible magical pull acting instantaneously across empty space. Space-time itself is carrying physical information. Space is not nothing. It is a physical structure that can be affected, distorted, and transmit effects across the universe. Before Einstein, most physicists believed time operated the same everywhere in the universe. 1 second on Earth would be 1 second anywhere else. Time was seen as a giant invisible clock running steadily behind everything in reality. Newton thought that way, Maxwell thought that way, and honestly, human intuition thought that way too. That idea sounds completely reasonable. You look at a clock, the second hand moves steadily. Everything seems stable and absolute. But then Einstein appeared and nearly destroyed that entire intuition. In 1905, with special relativity, and then in 1915 with general relativity, he put forward one of the strangest ideas ever to appear in the history of science. Time is not fixed. It can change. It can be stretched. It can run faster or slower depending on gravity and motion. This is where gravity begins to behave in ways that are almost absurd. According to general relativity, clocks in strong gravity run slower than clocks in weak gravity, not appear to run slower. I am talking about time actually flowing more slowly. A clock placed at sea level technically runs slower than a clock on top of Mount Everest, which is about 8,848 meters high. This effect is extremely small for everyday life, but it is real and has been measured with atomic clocks in the 20th century with astonishing accuracy. That means two people standing at two different heights on the same planet are actually experiencing two slightly different versions of time. I always find that both funny and intellectually unsettling. You just need to go up a high mountain, and reality has already started working a little differently. Einstein explained this with space-time curvature. Massive objects like planets or stars curve space-time. And the closer you are to a region of strong space-time curvature, the slower time flows. This is no longer gravity in the sense of a mysterious pulling force, like in Newtonian intuition. Gravity began to resemble the geometry of reality itself. Imagine space-time like an invisible landscape. The more massive an object is, the deeper that landscape is dented. Everything, including light and clocks, has to travel along that distorted geometry. Honestly, that is one of the most beautiful ideas in physics. Gravity is no longer a simple force. It is the structure of space-time. Mercury is the famous example of this. That planet orbits very close to the sun, much closer than Earth, so the space-time curvature around Mercury is significantly stronger. 19th century astronomers noticed a small deviation in Mercury's orbit called perihelion precession that Newtonian gravity could not fully explain. For many years, that was an uncomfortable problem for classical physics. Then Einstein appeared, wrote down the equations of general relativity, and that deviation appeared almost perfectly. That was the moment many physicists realized gravity was not what we had thought. But what was truly destabilizing was not in Mercury. It was in the consequences of the whole thing. If gravity determines the speed of time, then the universe does not have a single master clock common to everything. There is no absolute time flowing steadily somewhere outside the cosmos. Your time depends on where you are standing, how strong the gravity around you is, and how you are moving through space-time. That means reality is not stable in the way human intuition once believed. Time is not a fixed stage where the universe plays out. It is part of the physical universe itself. It can be stretched, slowed down, and distorted. Honestly, that is where physics starts to look like science fiction, even though all of it is experimentally verified. And if you think gravity distorting time is strange enough, wait until motion enters the story. Because when objects move really fast, time behaves in even stranger ways. When Einstein published special relativity in 1905, he did not just change how we understand light or motion. He did something far stranger. He made time dependent on velocity. According to the theory, a moving clock runs slower than a stationary clock. And this effect becomes stronger the closer an object moves to the speed of light, about 299,792 kilometers per second. Honestly, this is one of the ideas that makes human intuition nearly revolt. Because our entire everyday experience tells us that time is simply time. 1 minute is 1 minute, 1 second is 1 second. But the universe does not work that way. In relativity, time is more like part of geometry than an absolute flow. The faster an object moves through space, the slower it moves through time. This sounds almost absurd until you look at the evidence. One of the most beautiful pieces of evidence comes from cosmic ray muons. Muons are unstable particles created when cosmic rays from space collide with Earth's upper atmosphere. They have an extremely short lifetime, about 2.2 microseconds. By ordinary intuition, they should decay long before reaching the ground, but they still appear around us all the time. The reason is that they are moving near the speed of light. Time for them flows slower than for us. From their perspective, they have not lived long enough to decay. Honestly, I have always liked this example because it shows that relativity is not philosophical speculation. It is particle physics measured in the laboratory. A tiny particle is literally experiencing a different time from you simply because it is moving fast enough. The universe allows that to happen. And once you accept that, the old intuition about reality begins to collapse very quickly. The astronauts on the Apollo missions also technically experienced time differently from people on Earth. The effect was very small, extremely small, but measurable with precise atomic clocks. When the spacecraft moved at high speed around Earth and the Moon, the clocks on board did not run exactly like the clocks on the ground. In space travel, two relativistic effects occur at the same time. Special relativity slows time due to velocity, while general relativity makes time run a little faster when gravity weakens at greater distances from Earth. The interesting thing is that these two effects sometimes compete with each other. The universe is like it is constantly adjusting the speed of time, depending on geometry and motion. That is what makes relativity both beautiful and unsettling. You can no longer separate space, time, and gravity. They are locked together into a single system. Satellites in orbit also have to account for relativistic corrections. If they did not, navigation systems would gradually accumulate significant errors. This is extremely important because it shows that relativity is not science fiction or abstract philosophy for mathematicians. It is experimentally verified physics. You can measure it. You can build technology based on it. You can see its consequences in real engineering systems. Honestly, that is the part that makes me find gravity stranger than anything else in classical physics. Newtonian gravity views the universe as a fixed stage where forces pull objects back and forth. But relativity turns that entire stage into something dynamic, flexible, and deformable. Motion changes time. Gravity changes time. Massive objects change the geometry of space-time itself. And this leads to a very uncomfortable realization. There is no absolute time common to the entire universe. There is no cosmic master clock ticking steadily out there somewhere. Your time depends on where you are standing and how you are moving. Two different observers can genuinely experience reality differently without either being wrong. That sounds almost philosophical, but it is physics. Mercury orbits the sun differently from Newtonian predictions because space-time near the sun is more strongly curved. Light is bent near stars, not because gravity pulls it in the ordinary way, but because space-time itself has been changed. And that is where gravity begins to become truly strange to me. It no longer behaves like a normal force. It begins to resemble the very geometry of reality being bent. Honestly, when you look deep enough into gravity, you start to feel that we are no longer talking about a force. We are talking about the fundamental structure of the universe itself. And if that is true, then gravity may not be a force at all in the ordinary sense that humans once imagined. In Newton's model, gravity is a force acting at a distance. The sun pulls Earth. Earth pulls the moon. Everything sounds quite intuitive. You can imagine invisible forces pulling objects through empty space. And honestly, that model worked extremely well for hundreds of years. It was accurate enough to predict the orbits of planets, calculate eclipses, and ultimately help humans send the Apollo spacecraft to the moon. But Einstein looked at the problem in a completely different way. In 1915, with general relativity, he essentially reinterpreted all of gravity from the ground up. According to Einstein, gravity is not a force in the ordinary sense. Gravity is the curvature of space-time itself. I know that sounds more like science fiction than physics, but let's go slowly, step by step. The most common way to visualize this idea is the rubber sheet example. Imagine space-time like a huge stretched rubber sheet. If you place a heavy bowling ball on it, the sheet will dent. Then if you roll a small marble near the bowling ball, the marble will move along a curved path around the dented region. That is how many people explain gravity. The sun curves space-time, Earth moves through that curved region and forms an orbit. But here is the part I always find quite funny. This example is not perfect from the start. It uses gravity to explain gravity. The bowling ball dents the rubber sheet because gravity is pulling it down. So this model is only useful for visualization, not actual reality. What is more important is understanding the idea behind it. According to Einstein, planets are not being pulled around the sun by invisible strings. Earth is simply moving along the straightest possible path inside the curved space-time. That is the part that makes many people uncomfortable, because our intuition always thinks an orbit must require a continuous force pulling the object toward the center. But in general relativity, Earth is not really being pulled that way. It is following the geometry of space-time. Imagine you are walking on the surface of Earth. If you always walk straight according to your intuition, you will eventually return to the starting point because the planet's surface itself is curved. Einstein said space-time works similarly, except it is curved in 4 dimensions instead of 2. This turns gravity into something far stranger than an ordinary force. Space-time itself begins to behave like a real physical structure, rather than an empty stage where physics happens. Before Einstein, space and time were like the background, while matter was just the things moving inside it. After Einstein, the background itself can curve, distort, and change. Matter affects space-time, and space-time affects matter. The physicist John Wheeler later expressed it very beautifully. Mass tells space-time how to curve, and curved space-time tells matter how to move. Honestly, that may be one of the most beautiful ideas ever to appear in the history of physics. It turns gravity from a mysterious attractive force into the geometry of reality itself. This is also why Mercury's orbit differs from Newtonian predictions. Mercury orbits very close to the sun, so the space-time region around it is significantly more curved. It moves through that curved geometry, and its orbit deviates slightly. In a way, Newtonian gravity could not predict accurately. Einstein's equations predicted it almost perfectly. That was the moment many physicists realized general relativity was not just a mathematical trick. It described something physically real about the universe. But this is where the true intellectual amazement appears. If space-time can curve, then everything moving through space-time must follow that geometry. Not just planets, not just stars, but light too. This is the part that makes gravity start to look nearly impossible. According to ordinary intuition, light has no mass, so gravity should not affect it. But in general relativity, light does not need mass to be pulled. It simply moves according to the geometry of space-time, just like everything else. If space-time is curved near a massive object, light will follow that curved path. This leads to an extremely strange realization. Gravity does not only affect matter, it can also bend light itself. Light has no rest mass. In classical thinking, gravity should not affect it. If gravity were only an attractive force acting on mass, as Newton once described, then light should be completely immune. But the universe does not work according to that intuition. In general relativity, light is not pulled by gravity in the ordinary way. It simply travels according to the geometry of space-time. And if space-time is curved, then the path of light is also curved along with it. Honestly, this is one of the ideas that makes physics start to feel like something almost unreal. Einstein predicted this in 1915. He said that light from stars passing near the sun would be deflected by a very small angle because space-time around the sun is curved. This was an extremely bold prediction at the time. Many physicists thought it was too strange to be testable. But then in 1919, Arthur Eddington organized a famous solar eclipse expedition to test this prediction. During the eclipse, light from stars behind the sun could be observed more clearly. The result was astonishing. The positions of the stars were indeed deflected by almost exactly the amount Einstein had predicted. In just one night, Einstein became a global celebrity. But what was truly important was not the fame. What mattered was that the universe had just confirmed that gravity can bend light. Let's pause for a moment and think about that. Space itself is changing the path of the fastest thing in the universe. That means space-time is not an empty background. It is a real physical thing that can be distorted. And once you accept that, the entire cosmos begins to look different. Enormous galaxies can act like cosmic magnifying glasses. Their gravity bends light from objects behind them, creating a phenomenon called gravitational lensing. Instead of seeing light travel in straight lines, we see arcs, distorted images, and sometimes multiple copies of the same galaxy appearing in the sky. Honestly, that is one of the most beautiful things in astronomy. Gravity does not just hold the universe together. It also distorts the way the universe sees itself. Entire images of the distant cosmos can be stretched and bent by space-time curvature. But this is only the beginning of the strangeness. Once gravity is strong enough, it does not just bend light. It can prevent light from escaping completely. That is where black holes appear. To understand black holes, you first need to understand escape velocity. If you throw an object upward from Earth at too low a speed, gravity will pull it back. But if you reach about 11.2 kilometers per second, the object can escape Earth's gravitational field. That is the escape velocity. Every object with mass has its own escape velocity. The denser a massive object is, the higher its escape velocity. Now imagine an object so dense that its escape velocity exceeds the speed of light, about 299,792 kilometers per second. If nothing can move faster than light according to relativity, then even light itself cannot escape. That is a black hole. This idea became mathematically serious in 1916 when Karl Schwarzschild found the first solution to Einstein's equations describing an extremely dense object. From that came the concept of the Schwarzschild radius. If an object's entire mass is compressed inside this radius, it becomes a black hole. For example, if Earth were compressed into a sphere with a radius of only about 9 millimeters, it would become a black hole. The sun would need to be compressed to about a 3-kilometer radius. This sounds almost absurd, but the mathematics of general relativity allows it to happen. The boundary around a black hole, where light can no longer escape, is called the event horizon. You can think of it as a boundary beyond which information cannot return. Once you cross the event horizon, every path in space-time leads inward, not because the black hole is sucking everything with some mysterious force, but because the geometry of space-time has been curved so extremely that every future direction points toward the singularity. This is the point where ordinary intuition begins to collapse completely. Black holes are not cosmic vacuum cleaners as movies often portray. If the sun magically turned into a black hole while keeping its current mass, Earth would still orbit almost exactly as it does now. We would freeze from the loss of light and heat, but the orbit would remain nearly unchanged. Gravity at large distances still behaves normally according to the object's mass. What is truly terrifying about black holes is not that they suck everything. What is terrifying is that space-time near them becomes so extreme that ordinary intuition stops working. Near the event horizon, time slows dramatically for distant observers. If you watch an astronaut falling into a black hole, you would see their clock slow down, and then almost freeze at the event horizon. The light from them becomes redder and fainter until it almost disappears. But from the astronaut's own perspective, they continue falling normally. Two different observers can describe the same event in radically different ways without either being wrong. Honestly, this is where physics starts to feel like psychological horror for human intuition. Not only is space bent, not only is time distorted, even the concept of what actually happened begins to become unstable. And that is when the biggest problem appears. General relativity describes black holes beautifully at large scales. But near the singularity, where density becomes almost infinite, quantum mechanics begins to enter the picture. The two greatest foundations of modern physics begin to collide violently with each other there. And honestly, black holes may be where the universe is trying to tell us that we still do not truly understand how reality works. Einstein's general relativity works extremely beautifully at large scales. It describes stars, galaxies, black holes, and the entire large-scale structure of the universe with astonishing accuracy. Einstein's equations predict light being bent, time slowing near massive objects, the anomalous orbit of Mercury, and countless other phenomena almost perfectly. Honestly, it is one of the most beautiful theories ever to appear in the history of science. But on the other side of physics, quantum mechanics also works perfectly in its own way. It describes atoms, electrons, photons, and subatomic particles with almost absurd accuracy. Quantum electrodynamics, the theory that describes electromagnetism at the quantum level that I once worked on a lot, gives results so precise that prediction and experiment match to more than 10 decimal places. That is an almost absurd level of accuracy for any science. And that is exactly what makes the problem scarier. You have two extremely successful frameworks. One describes the universe at cosmic scales. One describes the universe at subatomic scales. Both are correct within their own domains. But when physicists try to combine them, the mathematics begins to collapse. Honestly, this is not the kind of we are just missing a few small equations. I am talking about the entire mathematical foundation starting to behave as if something fundamentally wrong exists. In quantum field theory, forces are usually described by carrier particles. Electromagnetism has the photon. The strong nuclear force has gluons. The weak force has W and Z bosons. By that logic, gravity should also have its own particle, commonly called the graviton. The idea sounds quite natural, but even into the 1980s, no one had ever observed a graviton in experiments. No detector had seen it. No observation had directly confirmed its existence. Gravity was almost refusing to behave like the other forces in nature. And this is where everything starts to become mathematically ugly. When physicists tried to quantize gravity in the same way as electromagnetism, the calculations often produced infinities everywhere. In quantum electrodynamics, infinities also appear, but we can handle them with renormalization. That is one of the most beautiful mathematical tricks of the 20th century. You reorganize the equations in a way that removes the infinities and still end up with extremely accurate predictions. But gravity does not cooperate that way. The infinities in quantum gravity calculations often cannot be removed cleanly and consistently. The equations almost explode mathematically. And what is extremely important is that this is not a small technical inconvenience. It is not like the computers are not powerful enough yet. It is a sign that something deeply incomplete exists in physics. The universe seems to be telling us that we are trying to combine two pictures of reality that are not entirely compatible with each other. Black holes make this problem much worse. General relativity predicts singularities, regions where density becomes infinite and space-time curvature becomes infinite. Honestly, whenever physicists see infinity appear in equations, it is usually a very big warning sign. It often means the theory has gone beyond its own limits. Singularities may be where the equations of relativity literally stop making sense. You can no longer clearly describe how space or time is working. Geometry itself begins to break down. And the scary thing is that quantum mechanics steps in exactly where relativity begins to collapse. The two strongest theories of modern physics almost collide head-on at singularities. This leads us to the Planck scale, about 10 mm³ meters. This is a scale so small it is almost impossible to imagine with human intuition. If a proton were blown up to the size of the entire observable universe, the Planck length would still be smaller than an atom in that model. At these distances, many physicists suspect that space-time itself is no longer smooth. It may become violent and unstable, something like a quantum foam, where geometry continuously fluctuates at microscopic scales. Think about that for a moment. Not only does matter or energy become uncertain at quantum scales, space and time themselves may begin to lose their ordinary meaning. Reality at the deepest level may be completely different from the way the human brain evolved to imagine it. Honestly, this is where physics starts to feel almost like psychological horror for intuition. In everyday life, space looks stable. Time looks continuous. Cause and effect look clear. But the deeper you look into gravity and quantum mechanics, the more the universe begins to behave as if those concepts are only approximations at large scales. And the problem is that in the 1980s, physicists still did not have a working theory of quantum gravity. We had ideas, we had mathematical attempts, we had speculation, but no one had a complete framework that was both consistent with quantum mechanics and consistent with general relativity. This is one of the biggest unsolved problems in all of science. Honestly, I have always been suspicious of people who speak too confidently about quantum gravity. If someone says they fully understand it, you should be extremely skeptical. Physics is nowhere near that level of certainty. And actually, one of the healthiest things in science is the ability to admit what we do not yet understand. Science does not advance by pretending to know everything. It advances by recognizing where current theories fail. Newtonian mechanics once looked perfect until relativity appeared. Classical physics once looked complete until quantum mechanics shattered the old intuitions. Maybe gravity is trying to tell us something similar once again. Maybe the problem is not just a few missing equations. Maybe physics itself is still incomplete in a much deeper way than we want to admit. The deeper I look into gravity, the more I feel that physics is trying to tell us something very uncomfortable. Maybe reality is completely different from what human intuition once imagined. And honestly, this is not the first time that has happened in the history of science. Every time physicists thought they had almost understood the universe, reality became stranger. Before Newton, people thought planets moved around Earth simply because that was natural. Then Newton appeared in 1687 and turned the cosmos into a giant mathematical system governed by laws of motion and gravity. For more than 200 years, Newtonian mechanics worked so beautifully that many people believed physics was almost complete. Then, at the beginning of the 20th century, Einstein appeared and nearly bent that entire picture. Space and time were no longer absolute. Gravity was no longer an ordinary force. Reality itself began to behave more like geometry than machinery. And almost at the same time, quantum mechanics appeared and destroyed the remaining intuition. Suddenly, particles were both waves and particles. Nature no longer operated by certainty, but by probabilities. Observation itself began to play a strange role in physics. Honestly, if you were a physicist living around 1890 and suddenly thrown into the 20th century, you would think the universe had gone insane. But the problem is, all those strange theories were correct. They worked. They predicted experiments with almost absurd accuracy. And that makes me suspect that gravity may be preparing to pull physics into another revolution. Maybe the entire current picture is still not the deepest layer of reality. Einstein spent the final years of his life pursuing the dream of a unified field theory, a framework that could connect gravity with the other forces in nature. He wanted to find a mathematical structure deep enough to explain the entire universe with a single set of unified principles. But Einstein never achieved that goal. Honestly, in his later years, physics had begun moving in directions that even Einstein did not like. Quantum mechanics became increasingly successful, but he was uncomfortable with its probabilistic nature. Einstein's famous line that God does not play dice actually reflected his very real discomfort with quantum reality. But the universe seemed not to care what humans found elegant or comfortable. And even into the 1980s, we still did not have any theory that truly unified gravity with quantum mechanics in a complete way. We had ideas, we had mathematical attempts, but there was no framework that was both experimentally verified and fully internally consistent. That is extremely important because modern physics describes the universe with two very different pictures. One smooth, geometric, and continuous picture from general relativity. One probabilistic, fluctuating, and quantized picture from quantum mechanics. And somewhere deep inside black holes or near the Planck scale, those two pictures begin to conflict violently. This leads to a very strange possibility. Maybe space-time itself is not fundamental. Think about that for a moment. In everyday life, we always consider space and time as the most basic background of reality. Everything happens inside space and time. But atoms were once considered indivisible until physicists discovered electrons, protons, and then quarks. Maybe space-time is the same. Maybe it is only an emergent phenomenon, something that arises from a deeper layer of reality that we still do not understand. Honestly, this is where physics starts to feel almost philosophical, but at the same time extremely technical. Physicists still do not know whether gravity should be quantized like the other forces or not. Maybe the graviton exists, maybe not. Maybe space-time is continuous. Maybe it is discrete at microscopic scales. Maybe geometry itself emerges from quantum information in some way that current physics has not yet reached. And the interesting thing is that we do not even know if we are asking the right questions yet. But this is what I truly like about science. Mystery is not a weakness of physics. Mystery is the fuel driving discovery. If everything were obvious and intuitive, science would have died long ago. The entire history of physics is the story of humans continually discovering that reality is stranger than their intuition. We began this story with gravity, the weakest force in nature. But then gravity turned out to have infinite range. It bends space-time, it slows time, it bends light, it creates black holes where reality itself almost collapses. And in the end, it may be pointing out that the entire current framework of physics is still not complete. Honestly, the universe clearly has no obligation to behave intuitively. Human intuition evolved to throw rocks, hunt, and avoid being eaten on a small planet. It was not designed to understand quantum fields or curved space-time. And I think that is what makes physics so beautiful. Not because we have fully understood the universe, but because the more we understand, the more we realize that reality is deeper, stranger, and far more interesting than we once imagined. The worst thing in science is not knowing the answer. The worst thing is thinking that you already know everything. Physics still has enormous mysteries waiting to be understood. What really makes me find gravity almost suspicious is the paradox we've been circling back to from the very beginning of this story. Gravity is the weakest force in nature, but somehow it controls the entire large-scale structure of the universe. Honestly, if you only look at physics at the level of atoms or particles, you would almost think gravity is not that important. Electromagnetism is horrifically stronger than it. The strong nuclear force is even stronger. But when you zoom out to the scales of stars, galaxies, and clusters of galaxies, gravity suddenly becomes the absolute king of the cosmos. And the reason for that is actually both simple and extremely strange. Unlike electromagnetism, gravity only attracts and never repels. Electric charge comes in two types, positive and negative. They can cancel each other out. A normal atom is almost electrically neutral because the number of positive protons and negative electrons is nearly equal. That means electromagnetic effects at large scales often cancel each other out. But mass does not work that way. There is no negative mass in the ordinary sense to cancel gravity. Every proton, neutron, and atom in the universe contributes gravity in the same direction. Gravity always adds up. That is extremely important. A single proton's gravity is almost meaningless. A hydrogen atom does almost nothing. But the universe contains about 1080 particles, and all of them are pulling in this direction. Honestly, gravity is like a terrifyingly patient force. It is weak, but it never shuts off and never cancels. Over billions of years, even tiny effects become enormous. After the Big Bang, the universe was mostly gigantic clouds of hydrogen and helium. At first, matter was distributed fairly evenly, but gravity began to work, very slowly, almost ridiculously slow by human standards. Small fluctuations in density caused some regions to have a bit more matter. Gravity in those regions became a little stronger. They pulled in more matter. And with more matter, gravity became even stronger. It was a runaway process that lasted for millions and then billions of years. Giant molecular clouds gradually collapsed under their own gravity. Temperatures rose, pressure rose, and eventually nuclear fusion began. A star was born. Our sun formed about 4.6 billion years ago in exactly that way. A gigantic cloud of gas and dust slowly collapsed until the central temperature was high enough for hydrogen fusion to start. Since then, the sun has been burning about 600 million tons of hydrogen every second to resist gravitational collapse. Honestly, stars are basically billion-year-long battles against gravity. And gravity almost always wins in the end. The sun contains about 2 times 10^30 kilograms of mass, roughly 99.8% of all the mass in the solar system. Its gravity dominates the entire region of space around us. Earth orbits the sun at about 30 kilometers per second. Jupiter, Saturn, comets, asteroids, all are held within the gravitational structure of the solar system by that enormous mass. But even the sun is just a fairly ordinary star in the Milky Way galaxy. And the Milky Way itself contains about 100 to 400 billion stars. Gravity holds all of them together despite enormous distances. Think about that for a moment. The stars in a galaxy are prevented from flying apart from each other by a force so weak that a small magnet on Earth can easily defeat it at local scales. Honestly, the universe somehow was built by persistence rather than brute force. Gravity is like someone who never gives up. It does not need to be strong. It just needs enough time. And the cosmos has given it billions of years. What is even stranger is that the universe seems extremely sensitive to the strength of gravity. If gravity were slightly weaker, matter might never collapse enough to form stars and galaxies. The universe might just be an endless dilute sea of hydrogen with no structure, no planets, no life. But if gravity were much stronger, stars could burn their fuel too quickly and collapse violently before planetary systems had time to stabilize. Galaxies could collapse too quickly into gigantic black holes. Somehow, nature landed in a narrow range where gravity is just weak enough that the universe does not destroy itself immediately, but also just strong enough to create structure. Honestly, this is one of the things that makes physics feel almost surreal to me sometimes. The entire cosmos depends on a force that is almost absurdly weak. A force that at human scales looks almost insignificant is the architect of galaxies, stars, and planets. But gravity does not just shape matter at large scales. It also determines the entire life cycle of themselves. Honestly, this equation is almost scary if you really think about it. It says that mass and energy are actually just two different forms of the same thing. And because the speed of light squared is such an enormous number, even a tiny amount of mass can create enormous energy. Every second, the sun converts about 600 million tons of hydrogen into helium. About 4 million tons of mass completely disappears every second and becomes heat and radiation. That is why the sun can shine continuously for about 4.6 billion years. But what is more important is that this energy creates outward pressure to resist the collapse caused by gravity. Stars exist thanks to an extremely delicate balance between the outward thermonuclear pressure and the inward pull of gravity. If thermonuclear reactions become too strong, stars will blow themselves apart. If gravity becomes too strong, they will collapse. The entire life of a star is a temporary equilibrium between those two things, and gravity never stops pressing inward. That is what matters. Thermonuclear fuel eventually runs out. Gravity never gets tired. Small stars like the sun can last for billions of years by burning hydrogen very slowly. But eventually, their cores begin to run out of fuel. When the outward pressure weakens, gravity begins to win. The outer layers swell into red giants and are eventually blown out into space. The remaining core collapses into a white dwarf. A white dwarf has a size close to Earth, but a mass close to the sun. The material inside it is so dense that a teaspoon of it could weigh tons on Earth. But even white dwarfs are not stable forever. In the 1930s, Subrahmanyan Chandrasekhar calculated that there is a limit for white dwarfs, about 1.4 times the mass of the sun, now called the Chandrasekhar limit. If the core of a star exceeds that limit, the quantum pressure of electrons is no longer enough to resist gravity. And this is where reality begins to behave in a very strange way. Normally, atoms are mostly empty space. Electrons exist very far from the nucleus compared to their own size. But when gravity becomes extreme enough, atoms no longer exist in the ordinary way. Gravity literally crushes matter beyond normal atomic structure. Electrons are forced into protons to form neutrons. The entire atomic architecture begins to collapse. Honestly, this is the part that makes gravity feel almost terrifying. A force weak at human scales can now crush entire stars to the point where chemistry itself stops existing. Even more massive stars are far more violent. When they run out of thermonuclear fuel, the collapse happens almost catastrophically. The core contracts at terrifying speed, temperatures skyrocket, and the outer layers are blown into space in supernova explosions brighter than entire galaxies. A supernova can release more energy in a few seconds than the sun produces in its entire lifetime. But what is scary is that even a supernova is not the end of gravity. After the explosion, if the remaining core is large enough, gravity continues to crush the matter further. And that is where the universe begins to create objects so dense that all ordinary intuition completely fails. Honestly, stars show you how patient and relentless gravity really is. It lets stars live for billions of years, then ultimately destroys them. The entire cycle of creation and destruction in the universe is controlled by the same weak force that you can easily defeat every time you stand up from a chair. That is almost absurd. But gravity does not care what sounds absurd to human intuition. It just keeps doing what it always does, pulling matter together, slowly but non-stop, until reality itself begins to behave differently. And in some places in the universe, gravity has compressed matter to the point where even atoms no longer exist in the normal way. When a massive star dies after a supernova explosion, gravity's story is not over yet. In fact, that is when gravity begins to show its most terrifying version. The remaining core of the star continues to collapse under its own weight. But at this point, matter no longer behaves in the ordinary way. Gravity is so strong that the entire atomic structure begins to be crushed. The result is one of the strangest objects in the universe, a neutron star. Honestly, neutron stars almost sound like something created by a physicist who stayed awake too long, rather than a real object existing in the cosmos. A neutron star can contain more mass than the sun inside a sphere only about 20 kilometers across. Think about that for a moment. You take an object nearly 1.4 million kilometers wide like the sun and compress almost all of its mass into a city-sized sphere. The density of the matter then becomes almost unimaginable. A teaspoon of material from a neutron star could weigh billions of tons on Earth. An amount of matter the size of a fingertip would weigh more than entire mountain ranges. Honestly, that is where human intuition almost completely gives up. But what is even stranger is how neutron stars are created. In ordinary matter, atoms are mostly empty space. Electrons exist around the nucleus in fairly stable quantum structures. But when gravity becomes extreme, the pressure inside the collapsing star increases to the point where electrons and protons are forced together. They combine into neutrons. The entire atomic architecture collapses. Atoms as we know them effectively stop existing. Matter inside neutron stars no longer resembles ordinary chemistry. It almost becomes one gigantic nucleus held together by gravity and neutron degeneracy pressure. Honestly, this is one of the things that makes the universe feel almost terrifying to me. Gravity is strong enough that it can destroy the entire structure that everyday reality is built on. Chemistry, solids, liquids, atoms, all begin to lose their ordinary meaning. You are no longer talking about matter in the familiar way. You are talking about nuclear matter compressed to near impossible densities. The surface gravity of neutron stars is about 100 billion times stronger than Earth's. If you somehow stood on the surface of a neutron star, it would be almost instantly impossible for the human body. One wrong step could crush you into something thinner than atoms. Even the height of a person standing upright becomes a problem. Gravity at the feet and head would differ enough to create terrifying tidal forces. Honestly, neutron stars no longer feel like places. They feel like environments where reality operates under completely different rules. Light escaping from neutron stars is also strongly affected by gravity. When light tries to leave that intense gravitational field, it loses energy and is pulled toward the red end of the spectrum. This is called gravitational redshift. Once again, gravity does not just pull matter. It also affects the very behavior of light and time. That always makes me feel strange in an almost poetic way. A city-sized object can distort reality around it to the point where photons themselves struggle to escape. But for physicists, neutron stars are extremely valuable. They give us rare glimpses of matter under extreme conditions impossible to create on Earth. No laboratory can create such densities or pressures. The universe naturally creates environments far more extreme than any experiment humans can build. And it is precisely in those places that physics begins to reveal behaviors we never see in ordinary life. Honestly, neutron stars are like enormous cosmic laboratories where nature is testing the ultimate limits of matter. But this is the truly disturbing part. Even neutron degeneracy pressure can eventually fail. In white dwarfs, electron degeneracy pressure resists gravity. In neutron stars, neutron degeneracy pressure continues to fight back. But gravity still does not stop. If enough mass continues to accumulate, even neutron matter is no longer enough to resist collapse. That means the universe has not yet reached the final limit of gravity. Honestly, this is the part that makes gravity start to look less like a force and more like an inevitability. It keeps pushing matter into ever more extreme states, layer of reality after layer, as if nature is continuously asking, can this survive any longer? And eventually, the answer always seems to be the same. If enough mass accumulates, gravity will destroy every form of resistance that matter ever had. Black holes sound more like something created by science fiction writers than something that actually exists in the universe. Honestly, if you told a 19th century physicist that there are regions of space where light cannot escape, where time almost freezes, and where space and time begin to swap roles with each other, they would probably think you had read too many weird novels. But what is most terrifying about black holes is that they are not products of imagination. They emerge naturally from Einstein's own equations. You do not need to try to invent black holes. The mathematics of general relativity almost pulls them out of the equations by itself. If enough mass collapses into a sufficiently small region of space, gravity becomes so strong that the escape velocity exceeds the speed of light. And because relativity says nothing can move faster than light, about 299,792 kilometers per second, that means even light itself cannot escape. That is exactly when a black hole appears. Honestly, I have always felt uneasy about the fact that the universe allows something like this to exist without violating any laws of physics. It is not a glitch in reality. It is a completely valid consequence of gravity. After Einstein published general relativity in 1915, Karl Schwarzschild almost immediately found a solution to the space-time around a spherical massive object. From that came the concept of the Schwarzschild radius. If an object's entire mass is compressed inside that radius, the object becomes a black hole. The Schwarzschild radius determines the size of the event horizon for a non-rotating black hole. What is strange is that this size is surprisingly small. If Earth somehow turned into a black hole, its event horizon would be only about 9 millimeters wide, the entire planet compressed into something smaller than a marble. But gravity at large distances would remain almost exactly the same because the mass has not changed. This is something many people misunderstand about black holes. They do not suck everything with some mysterious vacuum cleaner-like force. At large distances, black holes obey the same gravity laws as any other massive object. If the sun suddenly turned into a black hole while keeping its current mass, Earth would still orbit almost exactly as it does now. We would die from the loss of heat and light, but the planet orbit would barely change. What is truly terrifying about black holes is not that they suck everything in. What is terrifying lies in the structure of space-time around them. The event horizon is not a hard physical wall like in science fiction. It is a boundary in space-time beyond which information cannot return. Once you cross the event horizon, every possible future path leads inward, not because of some mysterious pulling force, but because the geometry of space-time itself has been distorted to the point where going outward is almost no longer a meaningful direction. Honestly, that is the part that makes black holes disturbing to human intuition. They do not just trap matter, they trap causality itself. If an object crosses the event horizon, it can no longer send information back to the outside universe, to the rest of the cosmos. That object has effectively disappeared. But what is even stranger is how time behaves near a black hole. To a distant observer, clocks near the event horizon slow down dramatically. If you watch an astronaut falling toward a black hole, you will see them move slower and slower, their light becoming redder and redder, until it almost freezes at the event horizon. But from the astronaut's own perspective, they continue falling inward completely normally. Two different observers describe the same event in two extremely different realities without either being wrong. Honestly, this is where relativity starts to feel less like physics and more like reality itself being bent. Black holes blur the boundary between space and time in an extremely bizarre way. Outside the event horizon, you can move freely in space, but cannot avoid moving forward in time. But inside the event horizon, the situation begins to reverse in a mathematical sense. The direction toward the singularity becomes something like your mandatory future. You cannot avoid plunging toward the center, just as you cannot avoid moving into tomorrow. Honestly, this is the part that makes even many physicists feel uncomfortable. Ordinary intuition becomes almost completely useless near black holes. And then you get closer to the singularity. This is where gravity becomes so extreme that the equations begin to lose ordinary physical meaning. Density theoretically becomes infinite. The curvature of space-time becomes infinite. And whenever infinities appear in physics, it is usually a very bad sign for the theory. Nature seems to be saying that our current mathematics has gone beyond its limits. Honestly, singularities always make me suspicious. I do not like infinities in physics. They usually mean we have missed something fundamental. Black holes are no longer simply objects sitting inside space. They become regions where space-time itself behaves pathologically. Geometry begins to collapse. The boundary between cause and effect becomes blurry. Ordinary concepts of distance and time begin to lose their familiar meaning. What is most disturbing is that general relativity predicts all of this extremely elegantly, but at the same time cannot fully explain what actually happens at the singularity. And that may be the biggest clue that relativity itself eventually breaks down. Because if your theory predicts a region where its own equations stop having physical meaning, Perhaps the universe is trying to tell you that there is still a deeper layer of reality that physics has not yet understood. The singularity is where physics begins to almost disintegrate before our eyes. Honestly, even the word singularity causes many people to imagine it wrong. Most people imagine it like an infinitely small dot somewhere inside the black hole, like an extremely tiny marble at the center. But in general relativity, the singularity is not necessarily a point in the ordinary intuitive sense. It is where the equations begin to produce infinite curvature of space-time. And whenever infinities appear in physics, it is usually not a sign that we have just found the ultimate truth of the universe. More often, it is a sign that our theory has gone beyond its own limits. Honestly, physicists are almost allergic to infinities. They usually signal that somewhere in the mathematics, something has gone terribly wrong. In a black hole singularity, density theoretically becomes infinite. The curvature of space-time becomes infinite. Gravity becomes infinite. And that is exactly the problem. Modern physics is built to describe measurable reality. Once everything turns into infinity, the equations begin to lose ordinary physical meaning. You can no longer clearly say what distance is, what time is, or how matter still exists in any familiar way. General relativity predicts singularities as almost inevitable whenever enough mass collapses under its own gravity. But at the same time, the theory itself almost admits that it cannot fully describe what actually happens there. Honestly, this is something I have always found both beautiful and frustrating in science. Nature seems to give us just enough information to recognize that a mystery exists, but not the complete answer. In the 1960s and 1970s, Roger Penrose and Stephen Hawking developed the famous singularity theorems. These theorems showed that singularities are not just weird mathematical accidents that appear in a few rare special cases. Under fairly general conditions, general relativity almost forces the universe to create singularities. If enough matter collapses under gravity, space-time eventually reaches a state where classical description breaks down. Honestly, that is an extremely unsettling conclusion. The most beautiful theory of gravity we have ever had predicts regions where it no longer works properly. Black holes become places where relativity predicts its own failure. And what is almost ironic is that gravity becomes strongest exactly where physics becomes least reliable. The closer we get to the most extreme region of gravity, the more the equations lose stability. It almost feels like the universe is deliberately hiding the deepest layer of reality from us. Honestly, sometimes I feel that nature has a very dry sense of humor toward physicists. Every time we think we are about to understand everything, the universe creates another layer of weirdness. Newton seemed complete until relativity appeared. Relativity looked magnificent until singularities and quantum mechanics began to break it. Nature clearly refuses to give us simple answers. But this is where things become even stranger. Singularities involve incredibly tiny scales. When matter is crushed to the extreme, distances begin to approach regions so small that ordinary ideas about space almost stop making sense. And that is exactly where quantum mechanics begins to enter the story. General relativity is a classical theory. It describes space-time as a smooth, continuous geometry. But quantum mechanics says reality at microscopic scales fundamentally fluctuates and is uncertain. These two pictures begin to collide violently near singularities. Think about it this way. General relativity handles gravity beautifully at large scales. Quantum mechanics handles atoms and subatomic particles beautifully at tiny scales. But singularities force both theories into a region where neither seems fully correct anymore. Honestly, this is where physics starts to feel almost unstable conceptually. Not only because the equations fail mathematically, but because ordinary intuition also completely collapses. At the singularity, ordinary ideas about before and after, inside and outside, even space and time themselves begin to lose their familiar meaning. And whenever physics reaches sufficiently tiny scales, quantum effects inevitably enter the story. You can no longer ignore the uncertainty principle. You can no longer pretend space-time remains perfectly smooth at arbitrarily small distances. Quantum fluctuations begin to matter. Reality at the microscopic scale no longer behaves like a smooth geometric fabric. It starts to look more like something restless, fluctuating, and fundamentally uncertain. Honestly, that is why many physicists suspect that singularities are not real physical objects in the final sense. They may simply be signs that classical relativity has reached its limit. Perhaps the singularity is not a truly infinite point, but only where current theories stop being valid. But to know what actually happens there, we need something beyond general relativity. We need to understand gravity at the quantum scale. And that is where the biggest battle in modern physics begins. Because at sufficiently small distances, quantum effects can no longer be ignored. Quantum mechanics is probably the most successful yet strangest theory that physicists have ever created. Honestly, if you try to explain quantum reality to someone who only knows everyday intuition, you will almost sound more like a madman than a scientist. In daily life, everything looks fairly reasonable. A ball has a definite position. It moves along a clear trajectory. If you know its speed and direction, you can predict its future quite accurately. Newtonian mechanics works very well at that scale. But then physicists began looking at atoms and subatomic particles, and reality suddenly stopped behaving normally. Electrons do not behave like tiny marbles moving in predictable orbits. They do not orbit the nucleus like planets around the sun, as many old textbooks used to illustrate. Quantum mechanics describes electrons with wave functions, mathematical structures that resemble probability clouds more than ordinary tiny objects. Honestly, this is where human intuition begins to collapse almost immediately. An electron does not simultaneously have a perfectly definite position and velocity the way ordinary objects do. In 1927, Werner Heisenberg developed the famous uncertainty principle. This principle says you cannot simultaneously know both the exact position and momentum of a particle. The more precisely you measure position, the more information you lose about momentum. The more precisely you know momentum, the more uncertain position becomes. This is not because our instruments are not good enough. It seems to be a fundamental property of reality itself. Honestly, that is one of the things that makes the universe deeply strange to me. Nature does not operate like a completely deterministic machine, the way classical physics once imagined. At the quantum scale, reality begins to behave according to probabilities. Particles behave both like waves and like localized objects. In the famous double-slit experiment, electrons can create interference patterns like waves. But when you measure them, they appear as individual particles. Honestly, quantum mechanics almost makes you feel like the universe is refusing to give you a clear and stable picture of reality. You no longer have particle or wave in the simple sense. You have something stranger than both. And what is even more unsettling is that quantum mechanics does not predict certainty in the classical physics way. It predicts probabilities. The theory does not say an electron is definitely somewhere before measurement. It only gives a probability distribution of where you might find it. This once made many physicists uncomfortable, including Einstein. But the universe clearly does not care what feels intuitive to human minds. And despite all these bizarre implications, quantum mechanics works extraordinarily well. Honestly, that is the almost disturbing part. If quantum mechanics were only strange, we might have ignored it long ago. But it predicts experiments with almost absurd accuracy. Quantum electrodynamics, the quantum version of electromagnetism, is one of the most precise theories in the history of science. The precise measurements achieved in the 20th century are almost unbelievable. The magnetic moment of the electron was predicted accurately to more than 10 decimal places. Prediction and experiment match with a level of accuracy that almost no other field of science has achieved. That means no matter how strange quantum reality is, the universe clearly obeys it. And this is where the greatest frustration in modern physics appears. Electromagnetism has been successfully quantized we have the photon, we have quantum field theory, we have mathematics that works astonishingly well, but gravity refuses to cooperate in the same way. Physicists can describe atoms very beautifully. We can predict chemical behavior, semiconductor physics, lasers, and nuclear interactions with extraordinary accuracy. All of modern technology depends on quantum mechanics. But somehow, gravity still stands outside all of that, like an outsider stubbornly refusing to fit into the framework. Honestly, gravity almost behaves as if it never received the instruction manual explaining how the rest of physics works. Every other fundamental interaction eventually fits into quantum field theory in some way. Gravity keeps resisting. When physicists try to quantize gravity like electromagnetism, the mathematics often explodes into infinities that cannot be handled consistently. And that is not a minor inconvenience. It almost feels like the universe is saying that space-time itself cannot simply be treated like ordinary quantum fields. That is especially disturbing because gravity is not just another force acting inside space-time. According to general relativity, gravity is the geometry of space-time itself. And if that very geometry must become quantum in some way, then perhaps the entire idea of space and time needs to be rethought from the ground up. Honestly, this is where physics starts to feel less like solving equations and more like trying to understand a reality fundamentally alien to human intuition. Quantum mechanics has destroyed classical certainty. Gravity has destroyed the idea of fixed space and time. Combining both may require concepts stranger than anything physics has ever created. Perhaps space-time itself is not fundamental. Perhaps geometry emerges from a deeper layer of reality. Perhaps at extremely small distances, familiar concepts of distance and time lose all meaning. And that is why many physicists believe that quantum gravity will not just be general relativity plus quantum mechanics. It may require completely new ideas about reality itself. In everyday life, space looks smooth and continuous. You can divide a distance into smaller and smaller parts without any problem. Time is the same. It feels like a stable and continuous flow. But modern physics is beginning to suggest that at extremely small scales, that entire picture may collapse completely. This is where the Planck scale appears. Max Planck, one of the founders of quantum mechanics, realized that from the fundamental constants of nature, one could construct a special unit of length, now called the Planck length. Its value is about 1.6 times 1035 meters. Honestly, this number is almost impossible to imagine with human intuition. If a proton were blown up to the size of the entire observable universe, the Planck length would still be smaller than an atom in that model. It is far smaller than anything the evolved human brain ever needed to understand. And the worrying thing is that below the Planck scale, our current physics equations begin to lose reliability. General relativity describes space-time as a smooth and continuous geometric structure. Quantum mechanics says reality at microscopic scales is full of fluctuations and uncertainty. When you approach the Planck scale, those two pictures begin to collide violently with each other. Gravity becomes strong enough that the quantum effects of space-time itself can no longer be ignored. Honestly, this is where physics starts to become almost conceptually unstable. Quantum fluctuations at that scale could distort space-time dramatically. Instead of a smooth fabric like in relativity, space-time might behave like a continuous microscopic storm boiling and fluctuating. The physicist John Wheeler once used the term quantum foam to describe this idea. Imagine reality at the smallest scales is no longer smooth, but resembles the surface of a violently churning ocean. Tiny wormholes could appear and disappear continuously. The geometry of space could fluctuate non-stop. The difference between here and there, between before and after, may no longer be as stable as ordinary intuition thinks. Honestly, this is the part that makes gravity begin to feel almost alien to human understanding. Familiar concepts like distance and duration may no longer have clear meaning near the Planck scale. You can no longer simply say, this is an exact position, or this is a definite period of time. The very structure of space-time may become uncertain at a fundamental level. This is especially strange because all of classical physics was built on the assumption that space and time are a stable background where all events take place. But near the Planck scale, that very background begins to fluctuate. Reality almost stops behaving like a fixed stage and starts to resemble a restless process that is constantly changing. Honestly, this is where human intuition almost completely gives up. And the problem is that throughout the entire 20th century, no experiment could directly probe such scales. To reach the energies corresponding to the Planck scale, you would need particle accelerators far beyond anything humanity has ever built. The relevant distances are too small, and the required energy is too extreme. That means physicists are stuck in an extremely frustrating situation. We know our current theories collapse near the Planck scale, but we cannot directly observe what actually happens there. This is one of the major reasons why quantum gravity remained unsolved in 1988. Honestly, physics had almost hit a wall. We have extraordinary theories that describe most of reality with astonishing accuracy, but at the deepest levels, the universe still refuses to reveal its true structure. And that leads to a very strange possibility. Perhaps we need completely different mathematical frameworks to understand these regions. Maybe space-time is not the ultimate fundamental object of reality. Maybe the geometry of space itself emerges from a deeper layer of reality. In the history of physics, many things once considered fundamental later turned out to be emergent phenomena, arising from something else. Temperature turned out to emerge from the microscopic motion of atoms. The solidity of matter turned out to be mostly the result of electromagnetic interactions and the empty space inside atoms. Perhaps space-time is the same. Maybe space and time are not the final foundation of the universe, but only a large-scale approximation of something much deeper and far stranger. Honestly, that is a thought that is both exciting and disturbing. All of human intuition evolved in a world where space and time appear stable. Our brains are optimized for throwing rocks, hunting, and avoiding danger on the African savanna, not for understanding quantum foam near the Planck scale. The universe clearly has no obligation to behave according to the intuition of creatures like us. And gravity seems to be the force that keeps pushing physics to confront that truth. The more we study gravity, the more we discover that reality resembles less of a mechanical machine and more of a strange multi-layered structure, where each deeper layer destroys the assumptions of the layer above. Newton destroyed the old intuition about celestial motion. Einstein destroyed absolute space and time. Quantum mechanics destroyed certainty itself. And perhaps gravity at the Planck scale is trying to tell us one more uncomfortable truth. Reality may be built in a way completely different from what human intuition expects. Einstein spent most of his later years pursuing a dream that physics had still not achieved by the 1980s. He wanted to find a unified field theory, a system deep enough to explain all the forces in nature with the same fundamental mathematical structure. Honestly, that was an intellectually almost terrifying ambition. After creating general relativity and completely changing how humanity understood gravity, Einstein did not believe that reality was truly divided into separate pieces as physics at the time was describing. He hoped that electromagnetism, gravity, and perhaps all other forces were ultimately just different manifestations of the same deeper structure. In a sense, he was trying to find the secret grammar of the universe. But no matter how extraordinary his intellect, Einstein never completed that goal. That has always struck me as both fascinating and humbling. One of the greatest minds in the history of science spent decades of his later life pursuing an idea he could never fully solve. Honestly, that is also a very important reminder about science. Intelligence alone does not guarantee that the universe will reveal its secrets to you. Reality has no obligation to be simple just because humans want it to be elegant. And even into the 1980s, physicists still did not have a successful unification between gravity and quantum mechanics. We have extraordinary theories that describe most of nature with astonishing accuracy, but the deeper we look, the more contradictions appear. General relativity describes space-time beautifully at large scales. Quantum mechanics describes microscopic reality with almost absurd precision. But somewhere near black holes, singularities, and the Planck scale, those two pictures begin to collide violently with each other. Honestly, I think one reason this problem is so difficult is that many scientists, even the most brilliant ones, sometimes underestimate the true level of strangeness of reality at those deep levels. Human intuition always wants the universe to behave sensibly. We want clear pictures, stable laws, and a predictable reality. But the history of physics has almost always gone in the opposite direction. Aristotle once thought everything naturally sought its proper place. Newton destroyed that picture with laws of motion and universal gravity. Then Einstein destroyed Newton's absolute concepts of space and time. Then quantum mechanics destroyed the very idea that nature always operates deterministically. Each major revolution in physics has almost always forced humanity to abandon a previously very comfortable intuition. Honestly, that is an extremely interesting pattern in science. The deeper you look, the less reality resembles everyday human experience. And that makes me suspect that future revolutions may be equally shocking. If a 19th century physicist suddenly woke up inside modern quantum physics, they would probably think the universe had gone insane. But from the perspective of future physics, perhaps we ourselves are currently missing something enormous. Maybe space-time is not the final foundation of reality. Maybe gravity is only an emergent phenomenon from something deeper. Maybe quantum mechanics itself is only an approximation of an even stranger layer of reality. Honestly, whenever physicists become too certain that current theories are nearly complete, history usually prepares another surprise. Science does not advance by certainty. It advances by discovering exactly where current ideas fail. Newtonian gravity failed near extreme speeds and strong gravitational fields. Classical physics failed inside atoms. General relativity may fail near singularities. Quantum field theory may fail near the Planck scale. Every failure becomes a clue, and gravity seems to contain more clues than any other force. It is absurdly weak at human scales, yet it controls the structure of the entire cosmos. It bends space-time. It changes the flow of time. It creates black holes, where the equations themselves begin to collapse. And whenever physicists try forcing gravity into the same framework as the rest of quantum physics, mathematics starts resisting violently. Honestly, gravity almost behaves less like normal force and more like a message from reality saying, "You still do not understand the deepest structure yet." Perhaps that is why Einstein spent so many years chasing unification. He sensed that beneath all the equations, something more fundamental was still hidden underneath. For most of the history of physics, scientists usually assumed that space-time was a fixed stage on which all events in the universe took place. Objects move in space, events occur in time, gravity acts inside space-time. The entire structure of classical physics was built on that intuition. Space and time were seen as the basic foundation of reality. But the more we study gravity, especially near black holes and quantum scales, the more physicists begin to ask a very uncomfortable question. What if space-time itself is not the ultimate fundamental thing? Honestly, this is the kind of question that has repeatedly changed the entire history of science. In the past, people always thought they had reached the final layer of reality, only to later discover that there were still deeper structures below. Atoms were once considered indivisible. The very word atom in Greek even means cannot be cut further. But then physicists discovered electrons, protons, and neutrons. Later, protons and neutrons were found to be made of quarks. The entire picture of matter kept breaking down into deeper layers. And that makes many physicists suspect that space-time may someday be viewed the same way. Perhaps space and time are not the final foundation of the universe, but only emergent phenomena arising from a deeper layer of reality that current physics does not yet understand. Honestly, gravity is the big reason why this possibility deserves to be taken seriously. Gravity behaves differently enough from the other forces to be almost suspicious. Electromagnetism fits very beautifully inside quantum field theory. The strong nuclear force and weak nuclear force also eventually found consistent quantum descriptions. But gravity keeps resisting every attempt at full quantization. And that is not just a small mathematical inconvenience. It almost feels like nature is trying to say that space-time itself cannot simply be treated as another ordinary field. Perhaps the entire framework we are using to think about reality is not deep enough. Ordinary geometry works extremely well at human scales. Euclid's geometry describes everyday space very well. Newtonian intuition works beautifully for moving objects at ordinary speeds. Even general relativity works astonishingly well at large cosmic scales. But at microscopic scales, things begin falling apart. Near the Planck scale, space-time may fluctuate violently. Distances may lose precise meaning. Cause and effect themselves may blur in strange ways. Honestly, the deeper you look into the universe, the less reality resembles the world that human intuition evolved to navigate. And that actually should not be so surprising. The human brain evolved to survive on the African savanna, to avoid predators, throw rocks, and recognize faces. It did not evolve to understand black holes, quantum fluctuations, or curved space-time. Human intuition is survival machinery, not a cosmic truth detector. Honestly, I always find it funny when many people become emotionally uncomfortable, when physics stops feeling intuitive. The universe clearly did not design itself to make sense to primates walking around on one small planet. There is no reason why reality at the deepest scales should resemble everyday human experience. If anything, the history of science repeatedly shows the opposite. Every major breakthrough almost always reveals that reality is stranger than our initial intuition. Earth is not the center of the cosmos. Time is not absolute. Particles do not behave like tiny eyeballs. Gravity is not an invisible pulling force the way Newton once imagined. And perhaps future physics will continue destroying assumptions even further. Honestly, I think mystery should not discourage curiosity. It should intensify it. Some people hear about quantum mechanics or black holes and conclude that the universe is too weird to understand. I think the opposite. It is precisely because reality is so strange that science becomes worth doing. If the universe behaved exactly as common sense predicts, physics would become boring very quickly. The entire excitement of science lies in the fact that nature keeps surprising us. And gravity is probably the biggest source of surprise in all of modern physics. It is absurdly weak at human scales, yet it shapes galaxies, stars, black holes, and the large-scale structure of the cosmos. It bends light, slows time, and creates singularities where our current equations collapse. One of the biggest misunderstandings about science is that many people think it is like a collection of final answers, as if physicists somewhere are keeping a secret book containing all the truths of the universe. Honestly, science is almost the complete opposite. Science not advanced by absolute certainty. It advances by doubt, uncertainty, and the ability to admit when current ideas no longer work. Every major advance in physics almost always begins with someone realizing that reality refuses to behave exactly as the old theory predicted. Newton's gravity is a perfect example. For more than 2 centuries, it worked extremely well. It explained the motion of planets, falling objects, tides, and nearly all celestial mechanics with astonishing accuracy. If you lived in the 19th century, you would probably think Newton had solved gravity forever. But eventually, small discrepancies began to appear. Mercury's orbit did not completely match Newton's predictions. The speed of light behaved strangely. Electromagnetism did not fit perfectly with classical mechanics. And instead of ignoring those problems, Einstein took them seriously. Honestly, that is one of the things I admire most about the great physicists. They do not worship theories. They follow reality even when reality becomes uncomfortable. Einstein succeeded not because Newton was wrong in a simple sense. Newton's gravity still works very beautifully under countless ordinary conditions. We still use it to launch spacecraft and calculate orbits. But relativity explains phenomena that Newtonian mechanics cannot fully handle, especially near extreme speeds and strong gravitational fields. That is extremely important to understand. In science, old theories often do not become useless. They become approximations within larger frameworks. Newtonian mechanics is an approximation of relativity at low speeds. Classical physics is an approximation of quantum mechanics at large scales. And someday, future physicists may replace parts of relativity in the same way relativity once replaced parts of Newtonian mechanics. Honestly, I think that is an emotionally difficult idea for many people. Humans naturally want certainty. We want stable truths and final answers. But nature clearly does not promise those things. Each time physics goes deeper, the universe becomes stranger and forces us to revise assumptions that were once considered obvious. That is not a weakness of science. That is its strength. Science is a continuous self-correcting process. Admitting ignorance is not failure in physics. It is intellectual honesty. Honestly, whenever someone claims complete certainty about reality, especially in deep physics, you should immediately become suspicious. The universe has already embarrassed too many confident people. Aristotle sounded certain. Newton sounded certain. Even Einstein sometimes sounded certain. But reality always turned out to be deeper, stranger, and less intuitive than expected. And at present, we are still surrounded by unsolved mysteries. Singularities are still deeply problematic. Quantum gravity still does not exist as a completed theory. We still do not know whether space-time itself is fundamental or emergent. We still do not know what actually happens inside black holes. We still cannot reconcile general relativity with quantum mechanics in a fully consistent way. Honestly, that should not discourage curiosity. It should intensify it. One of the most beautiful things about science is that every answer usually creates even deeper questions. When Newton unified celestial motion and falling objects under gravity, it once looked revolutionary. Then Einstein revealed that gravity was not actually an ordinary force, but curved space-time. Then quantum mechanics showed that microscopic reality does not even obey ordinary deterministic intuition. And now gravity itself may be suggesting that the entire concepts of space and time need to be rethought once again. Honestly, physics sometimes feels less like climbing a mountain toward final truth, and more like entering deeper rooms inside an endless labyrinth. But that is exactly what makes it exciting. If the universe were simple enough to fit neatly inside ordinary human intuition, science would have ended long ago. Instead, each generation discovers that reality is more complex than the previous generation imagined. Gravity is one of the greatest examples of that. It is absurdly weak compared to the other forces at human scales, yet it shapes galaxies, stars, black holes, and the large-scale structure of the cosmos. It bends light, slows time, and creates singularities where our own equations collapse. If you look back at this entire journey, the most astonishing thing about gravity is the way it continuously destroys our initial intuitions about reality. We began with an almost absurd paradox. Gravity is the weakest force in nature that physics knows about, yet somehow it controls the entire large-scale structure of the universe. A small magnet can defeat the gravity of the entire Earth in a simple experiment, but it is gravity that shapes galaxies, stars, planetary systems, and black holes. Honestly, right from the start, gravity already felt almost suspicious. It is weak to the point of absurdity at human scales, but over the billions of years of cosmic time, it becomes the architect of the entire cosmos. And then everything only became stranger from there. Newton gave humanity an extremely beautiful mathematical description of gravity, but even Newton never explained what gravity truly is. Then Einstein completely changed that picture. Gravity was no longer an invisible pulling force acting across empty space. It became the very curvature of space-time. Massive objects distort the geometry of the universe, and matter simply follows the straightest possible paths inside that curved structure. Honestly, that was one of the greatest conceptual revolutions in the history of science. Space and time were no longer a passive background. Reality itself became dynamic. Even geometry became physics. But gravity was not done destroying our intuitions there. Light, which has no rest mass, is still bent by gravity. Time itself slows down near massive objects. Two clocks in different gravitational regions actually experience different amounts of time. Black holes emerge naturally from Einstein's equations, creating regions where even light cannot escape. And near the singularities, the curvature of space-time theoretically becomes infinite. Honestly, the deeper you look, the less gravity resembles an ordinary force, and the more it resembles a crack in our very understanding of reality. Black holes show the limits of relativity. Quantum mechanics shows the limits of classical intuition. And somewhere between the two, physics begins to break down. Quantum mechanics says that microscopic reality behaves according to probabilities, uncertainty, and is often almost absurd compared to everyday intuition. Relativity says that space and time are not fixed but flexible. But when physicists try to fully combine those two pictures, the mathematics begins to collapse into infinities and contradictions. Honestly, that is a situation that is both uncomfortable and beautiful. We possess equations that can predict experiments with astonishing accuracy, but we still do not fully understand what reality truly is at the deepest level. That contrast has always fascinated me. Humans often think knowledge means certainty, but science continuously shows the opposite. We can calculate extraordinary things while still not fully understanding the deepest nature of what we are calculating. We can launch spacecraft across the solar system using extremely precise gravity calculations while still not knowing what gravity ultimately really is. And part of the reason this unsettles us lies in human intuition itself. Common sense evolved to help us survive, not to discover cosmic truth. The human brain evolved to recognize patterns, avoid danger, and survive long enough on a small planet. It did not evolve to understand quantum fields, curved space-time, or singularities. Honestly, I think many people underestimate how limited human intuition is. We instinctively want reality to resemble everyday experience because that is the only scale our brains evolved to handle. But the universe clearly has no obligation to behave according to the expectations of primates living on a small planet. And the history of physics continuously proves that reality is always stranger than our initial imagination. Earth is not the center of the universe. Time is not absolute. Particles are not simply particles. Gravity is not simply a force. Space may not even be the ultimate foundation. Each deeper layer of discovery almost always destroys some old familiar assumption. Honestly, that is one of the most astonishing things about science. The deeper you study nature, the less intuitive the universe becomes. But I do not think mystery should reduce curiosity. It is exactly the opposite. Mystery is evidence of how rich nature is. If reality worked exactly as common sense predicts, science would have become boring centuries ago. Instead, each generation discovers that the universe is stranger, deeper, and more beautiful than the previous generation imagined. Gravity is probably the most perfect example of this entire process. A force so weak it is almost absurd at human scales ultimately shapes galaxies, stars, black holes, space-time, and perhaps the final fate of the cosmos. And despite centuries of study from Newton, Einstein, and countless other physicists, gravity still refuses to fully reveal its true nature. One thing I have always found interesting is that many people start to feel uncomfortable the moment physics stops giving intuitive answers. As long as the universe behaves like everyday experience, people feel fine. A ball falls to the ground, a car moves, planets orbit stars. That sounds reasonable. But then physics starts saying that time can slow down, space can curve, particles can behave like waves, and black holes can trap both light and information. And suddenly, many people want science to go back to normal. Honestly, I have always thought the more interesting reaction should be excitement rather than discomfort. Personally, I find uncertainty far more interesting than fake certainty. A completely predictable and fully understandable universe would be a very boring universe. What makes science beautiful is the fact that reality is always deeper than what we previously expected. Gravity is the perfect example of that. After centuries of extraordinary research, gravity is still full of mystery. We can predict the motion of planets with astonishing accuracy. We can calculate orbits to send humans to the moon. Humanity went from Newton's equations in 1687 to the moon landing in 1960. We learned how to build rockets, nuclear reactors, computers, and spacecraft. But despite all that progress, we still do not fully understand what gravity truly is at the deepest level. Honestly, that is one of the most wonderful things about science. Knowledge grows enormously, but mystery somehow still exists alongside it. Real science does not pretend that mystery disappears just because the equations work well. A successful equation does not automatically mean we fully understand the deepest nature of reality. Newton's gravity worked excellently for centuries before Einstein revealed a deeper picture. And relativity itself may someday become part of an even larger framework. That is completely normal. Science is not a permanent finished monument. It is a continuous process of discovery. Each generation of physicists inherits unsolved questions from the previous generation. Newton inherited questions from Galileo and Kepler. Einstein inherited problems from Maxwell and Newtonian mechanics. Modern physicists inherit singularities, quantum gravity, and the very structure of space-time. Honestly, that is one of the reasons physics feels like a living intellectual adventure. No matter how much we learn, reality always seems capable of surprising us again. And I think curiosity is far more important than intellectual comfort. Some people want science to provide certainty because uncertainty makes them uncomfortable. But if you become too attached to certainty, you will stop seeing reality clearly. Science works precisely because physicists are willing to question even the most successful ideas when experiments demand it. That requires humility. It requires the ability to say, perhaps our current picture is still incomplete. Honestly, that is not a weakness. That is strength. The moment science stops doubting itself is the moment it stops being science. And that is why I always want people not to fear uncertainty in science. Uncertainty does not mean knowledge is useless. It means reality is deeper than what we currently understand. There is something profoundly exciting about living in a universe that is still full of unanswered questions. It means discovery is still possible. It means future generations may uncover ideas stranger and more beautiful than anything we can currently imagine. And history shows that this will almost certainly continue to happen. After all, nearly every major revolution in physics once sounded absurd before evidence forced humanity to accept it. The idea that Earth orbits the sun once sounded absurd. Curved space-time once sounded absurd. Quantum mechanics once sounded absurd. Yet reality keeps refusing to behave according to common sense. Honestly, that is probably the most important lesson gravity teaches us. The universe has no obligation to behave according to human intuition. Nature does not care what makes the primate brain living on a small planet feel comfortable. And honestly, I think that makes the cosmos far more beautiful, not less. Because it means reality is not limited by the boundaries of human imagination. Every time we think we have reached the final layer, physics reveals yet another deeper mystery lying beneath. Gravity turned out to be more than just objects falling. Time turned out not to be absolute. Matter turned out not to be truly solid in the ordinary sense. Space itself may not even be the ultimate foundation. Honestly, that is what makes physics feel like a grand human expedition rather than just memorizing facts. We are not just collecting information. We are slowly discovering how truly strange existence is. And I think that sense of wonder is far more important than a final answer. A final answer would end the adventure. It is the mystery that keeps it alive. Perhaps that is why I have always loved physics so much. Not because it provides certainty, but because it continuously destroys certainty in the most fascinating ways imaginable. And if gravity keeps teaching us one thing over and over again, it is the truth that the universe is always far smarter than we ever imagined. If you enjoy journeys where science makes reality stranger than science fiction, please subscribe to the channel and continue exploring the greatest mysteries of the universe with me. For now, always keep your curiosity alive, because the most wonderful thing about physics is that the universe is always far smarter than we ever imagined. and I will see you in the next story.